Okay, folks, why don't we go ahead and get started? So we have a quiz on Friday. We'll have a homework due on Friday morning. There'll be, so I'm available for appointments if you want to get help from me this afternoon. So Monday, Wednesday, 1 to 5 p.m. appointments. And once again, you just need to tell me, just tell me right after class that you'd like to come see me at some time this afternoon, and that's great. I mean, give me a time, but then that's great. And then there'll be a help session on Thursday evening we're going to move that to 7:30 p.m. At 36, and then that's on Google Meet. And you can get the link out of the syllabus like we've talked about before, like I've said before. That was really pretty well attended last week. I'm sure that was because the test was the next day, but if you were to attend this week, you could have an individual tutoring session. I'm happy to, the same thing with the 1 to 5 p.m. appointments. I'm happy to sit down with people and just give you practice problems if that's what you want, okay? So love to help you as much as possible in the class. There's also subject tutoring. You're paying for it already, so you should think about taking advantage of that if that is what would work best for you. We have great tutors over there. All right, so last time, any questions on the class actually before I move on? I have not yet, so if you've been looking on Inquire to see what your grade is, I was going to pull Achieve over after the test. I have not yet had the chance to do that. I will try to get that done in the next few days. If not that, the weekend, I'm going to pull your Achieve grades over, and then I'm going to take the Inquire system and make sure everything's weighted like it says in the syllabus. I'll let you know once that's happened. All right, so last time we were talking about ionization energies. All right, and so what were ionization energies? Anybody remember? Everyone, you remember? Yeah, the energy it takes to separate an electron from the atom. All right, and it always takes energy. You always have to put energy in to pull an electron away from an atom. Right, and let me say an isolated atom. All right, and remember the chemist term for isolated atom is gas phase, meaning you've got an atom by itself, there's large distances between it. Any other atom is just like anything in a gas. So let's think about those ionization energies and what we expect for that trend. This section we're in is about periodic trends, predicting things. All right, so predicting what we expect to see. So if I've got a sodium, and I'm going to make an ion with it. Sodium, does sodium want to give up an electron or does it want to gain electrons? Remember, everybody wants to be a noble gas. It wants to give up an electron, all right? So it still takes energy to pull the electron away when it's out and nothing's around it. You throw sodium in water and there are things around it that want that electron. If you throw sodium in water, I see some people smiling. If you've done this, it's super violently reactive, okay? Because the waters want the electron. So sodium, you have to give sodium a little bit of energy to give up its electron, but waters really want the electron, so a lot of energy is released when they grab the electron. Does that make sense? Okay. So sodium, you expect this ionization energy to be pretty small because it wants to lose that electron. How about chlorine? What's chlorine want to do? Does it want to lose electrons or gain electrons? It wants to gain electrons, so it's going to hold those electrons pretty tight. You expect this to be pretty high in terms of that. All right. So when we talk about what we talked about last or introduced last time as a first ionization energy, pulling the first electron away. This is going to be pretty small. This is going to be pretty large, and it's probably going to get larger as you go across. Okay. And so that indeed is the pattern we see when we look at the periodic table. If this is our periodic table here, like that, you're going to see that first ionization energies increase in this direction. Questions? Okay, now you can talk about other ionization energies. So here's this graph we had before that actually kind of demonstrates that as we go across the periodic table, right? Our first ionization energies are increasing. We talked about how the zigzaggy bit you can explain by half-filled and filled shells. But you'll notice that they increase as you go across the periodic table because as you get over to the right side of the periodic table, those atoms want to gain electrons so they can be like a noble gas. They can have the electronic configuration of a noble gas. And you'll see if we look here, as the atoms are smaller, it's harder to pull those electrons away. They're closer to the nucleus. They're feeling more of a nuclear charge. I'm going to use that argument here, and then I'm going to sort of give you an argument that's different for the next thing. And then here, as the atoms get bigger, right? We go down a row, the atoms get bigger because we're in a bigger shell for our outer shell electrons. That the first ionization energies are a little bit lower. Okay. All right, so the electrons aren't held quite as tight. Now we can talk about ionization energies other than first ionization energies. So there's first ionization energies, there's second ionization energies, there's third ionization energies. Looks like here we've got a fifth ionization energy, right? So what I'll do here is I'll circle this, we'll bring it over, and I'll go ahead and quickly type. Can everybody see this? Is that too small? Anybody have trouble seeing it? Okay, so I'm going to go ahead and make that bigger. Thank you for indicating that you were having trouble seeing it. Okay, and then I'm going to go ahead and say first ionization energy. Just to make it clear, that's this, and then I'm going to let you infer that that's second, third, fourth, fifth, if you're looking at this in the notes. But if we look at these ionization energies, so sodium has a first ionization energy, right? It wants to give up that electron. If you just look at that periodic table or the one that I handed out to you, if you can't see the periodic table from where you are. So after we give up our first ion, I'll walk over there. After we give up our first electron, not first ion, we end up with sodium has the electronic structure of neon, right? So it's happy. So what happens for our second ionization energy? It goes up 10 times. Do you see that? It's a lot of energy to take an electron away from it now, because now you're taking it away from the very stable electronic configuration of a noble gas. Does that make sense? All right, so if we look at the rest of these tables, right, magnesium, you take the first one away, okay, that took some energy. You take the second away, it took more energy. All right, always takes more energy to take the next one away, because you've got electrons around there, and as you take more and more electrons away, the effective charge on the nucleus is larger. All right. The model we used for effective charge actually didn't count the fact that you have other electrons you can think about the electrons, instead of thinking about an effective charge, you can think about, when I've got magnesium here and I have 2 electrons in these outer shells, they push against each other. They're both negative. They're going to repel each other, even though we're not counting that in our simple model. And so it makes it, once one's gone, now we've got a lonely electron out here, and it has, hold on, that's not going to work. It's still going to take more energy because it's not pushing against each other. Sorry, that model doesn't work. I'm going to go with a higher effective normal charge. All right. You remember, so in your homework there was this thing, Slater's rules, that I said we weren't going to learn. We're still not going to learn it, but it explains this better because it actually gives those electrons in the outer shell some shielding. Okay. So this second electron does shield. So this electron does shield that electron from the nucleus sum, and then once one of them's gone, you have less shielding. So that's a slightly better model. We teach you all sorts of models in this class, and we're trying to teach you the simplest models possible. And then as you go on in chemistry, if you go on in chemistry, we will continue to ratchet up the complexity of the models, and the models become more accurate. So that very simple model of nuclear, of Z effective that we taught here is good enough for our purposes, outside of having a little trouble right here, right, with this argument. But it's really good enough for our purposes. The Slater's rules is like a more complex model. There are more complex models than that, okay? But we're trying to stick with the simplest models possible and still have to have a model that works for what we need to do. Anyway, so good enough to just remember that every time you pull an electron away, it gets harder to pull the next one away, okay? All right, so so that happens here. We pull this one away, right? Takes some energy. Pull this one away. It takes more energy, right? Maybe twice as much energy. But what happens when we pull the third one away? Where we're here now, right? We pull 2 away from magnesium. We pull the third away, and it's really hard, right? Look at magnesium. Look across. See the pink? Because now we're going to take something and we're going to take it away from that very stable formation of being a noble gas, right? Full shells, half full shells are especially stable, and so you will see that in terms of these trends. Questions? Okay. So you need to know that every time you pull it, when every ionization energy we move up, every additional electron you pull away is going to take more energy, and then remember your full shells and half full shells with that noble gas column, which is a completely full outer shell, being super stable, being super extra stable. All right, then we're going to talk about electron affinity. And we're talking about all these things because they actually relate to the chemical reactivity of these atoms, right? Remember that our atoms touch the outside world with those outer shell electrons, and that's what determines what reacts with what bonds to what. So electron affinity. Electron affinity is the energy released, or actually you might gain it. You might have to put energy in to make it happen. The energy released or input, we'll say, to give an electron to an atom. All right, and I say input, but really, if we're talking about, you could calculate it with a computer, right? You could model it with a computer. How much energy would I have to give to this helium? Helium's a noble gas, right? Does it want more electrons? No, noble gas electron configuration is really stable. It's the outer shell. These things do not want electrons, all right? And so you can't, you see it's greater than 0? If you like throw an electron at helium, what it does, it just pops right back out. All right, so giving it an electron is difficult for helium, neon, the noble gases. It just doesn't happen in real life. Okay, so you can't measure it happening. So when I say input, yeah, we're not going to worry about that so much. What we're really concerned with is the amount of energy that's given off, which tells us something about how much that atom wants electrons, right? How much does fluorine want electrons? A lot, a little? A lot. Why? Periodic table, not the numbers. Yeah, it gets at the electron configuration of a noble gas, right? So it wants an electron a lot, and so it gives off a lot of energy. I want to introduce something to you that is a concept that you will see over and over and over again in chemistry. Greater than, when talking about energy, there's a convention we use. Plus is energy input or absorbed. I will probably switch to using absorbed because I like that better. And minus is energy given off. Okay? Just memorize that. I'm trying to think of it's just a convention. I'm trying to think of an explanation that makes better sense than it just is how people decided it and then they followed it. Okay? Just like there's a plus charge and a minus charge on your battery, right? Somebody decided which one was plus and which one was minus, but they're just kind of made up concepts. Yes?
So you said that the amount of energy they release increases the closer they get to noble gas, right?
Yes.
What's the deal with the nitrogen and phosphorus?
Oh, that's a really great question. So what's the deal? Why is this, especially nitrogen stands out, right? Why does nitrogen, why won't it take in a single electron, right? What was the answer?
It's a half shell.
It's a half shell. This is a half-filled shell. So if we think about nitrogen, we've got this is 1s, or 2s I can say here, that's full. And then our 2p has 3 orbitals, 1 electron, 1 electron, 1 electron, 1 for each of those 3 orbitals. It's a half-filled shell, and so it's hard to add 1 there. And then it gets easier again. That make sense? Okay. Which isn't to say that nitrogen doesn't take electrons from things. Okay, it does get up. We'll see in we're gonna do ions today, or what's our stable ions. Nitrogen will take on a 1, 2, 3 negative charge, so it can have the configuration of a noble gas. All right, and that's just in the context of what other things are going on around it. Okay, questions on those? All right, so we've got this electron affinity. We've also got